Everything you learned about how the world works is correct, and completely wrong at the same time. Not approximately wrong, not wrong at the edges, structurally wrong, in the sense that the rules governing the matter your body is made of, the light entering your eyes right now, the atoms in every object you've ever touched, those rules are fundamentally different from anything that feels intuitive, different in ways that still make me uncomfortable, and I helped write them. My name is Paul Dirac. I was there when quantum mechanics was being built, not just learning it, building it. I derived the equation that predicted antimatter before anyone had found it. I helped construct quantum field theory. I've spent my entire working life inside this framework. And I'm going to tell you plainly, quantum mechanics is the most precisely tested, most experimentally confirmed theory in the history of physics. And nobody fully understands what it means. Those two things are both true simultaneously, which is, appropriately, a very quantum situation. Let me start with why quantum mechanics had to exist at all. In the late 1800s, physicists tried to calculate how hot objects emit radiation. The theory they had, classical electrodynamics, perfectly good for everything else, made a specific prediction. As you go to shorter and shorter wavelengths, the emitted energy should increase without limit, to infinity. Every hot object in the universe should be catastrophically bright at ultraviolet frequencies. Obviously, they're not. You've looked at hot objects. They glow. They don't incinerate everything around them with infinite ultraviolet radiation. The classical prediction was not slightly off. It was infinitely wrong. Physicists called this the ultraviolet catastrophe, which is one of the more honest names in scientific history. Max Planck solved it in 1900 by proposing something he himself didn't believe, that energy doesn't come in continuous quantities. It comes in discrete packets, chunks. He called them quanta. He thought it was a mathematical trick to make the numbers work. He didn't think it was physically real. Einstein took it seriously. In 1905, he used the same idea to explain the photoelectric effect, the way light hitting a metal surface can knock electrons out. The details only made sense if light itself comes in discrete packets, particles of light, what we now call photons. But light is a wave. Everyone knew light was a wave. Maxwell proved it. You can demonstrate it with a diffraction grating in your kitchen. Light is clearly, demonstrably a wave. Except it's also a particle. Both, simultaneously. That contradiction, wave and particle, is not resolved in quantum mechanics. It's incorporated. And the clearest demonstration of what that means is an experiment simple enough to describe in a few sentences and strange enough to think about for the rest of your life. Fire electrons, single electrons, one at a time, at a barrier with two narrow slits. On the other side, a screen records where each electron lands. If electrons are particles like tiny bullets, you'd expect two clusters, one behind each slit. That's what bullets do. Instead, you get an interference pattern, alternating bands of high and low density across the entire screen, the unmistakable signature of waves interfering with each other. Even when you fire one electron at a time, with seconds between them, the pattern builds up. Each individual electron contributes one dot, but over thousands of electrons, those dots accumulate into an interference pattern. Each electron somehow interferes with itself, passes through both slits simultaneously, as a single particle. Here's the part that makes it worse. If you put a detector at the slits to find out which slit each electron actually goes through, the interference pattern vanishes. The electrons start landing in two clusters again, like bullets. Looking, just observing, changes what happens. I worked on the formalism that describes this. The mathematics handles it cleanly. What the mathematics is saying about what's physically happening, that's where things get genuinely difficult. The key concept is superposition, and I want to be precise about what it means, because the popular version is almost always wrong. Superposition does not mean we don't know which state it's in. It means the particle genuinely is in multiple states simultaneously. Before measurement, an electron doesn't have a definite position anywhere. It has a probability distribution, a spread of possible positions, all simultaneously real, described by what's called a wave function. The wave function is not ignorance. It's not a placeholder for information we haven't gathered yet. It is the complete description of the electron state. And that complete description includes no definite position. The act of measurement is what produces a definite outcome. Before measurement, genuine indefiniteness. After measurement, definite result. The transition between these, what's called wave function collapse, is one of the most debated topics in physics. We'll get to that. The evidence that superposition is real and not just we don't know? Quantum computers. A quantum computer uses qubits that exist in superposition of 0 and 1 simultaneously. The computational power of quantum computers comes precisely from this. They can perform many calculations in parallel because the qubits are genuinely in multiple states at once. If superposition were just ignorance, if the qubit were really in one state and we just didn't know which, quantum computers couldn't do anything a classical computer couldn't. They can. Superposition is real. Now, the uncertainty principle. This is almost always explained incorrectly, so let me be careful. The wrong version. You can't measure both position and momentum precisely because your measurement disturbs the particle. This implies the precise values existed before you measured, and your measurement messed them up. The correct version, position and momentum cannot both be precisely defined simultaneously. Not because measurement disturbs anything, because they are not both simultaneously real. This comes from wave mathematics. A wave that's precisely localized in space, a sharp spike, necessarily contains contributions from many different frequencies, many different momenta. Conversely, a wave with a precise frequency, a precise momentum, necessarily extends across all of space, completely undefined position. Position and momentum are complementary. The more precisely one is defined, the more genuinely undefined the other is, not unknown. Undefined. The precise value does not exist. This is a statement about the universe, not about our instruments. I derived similar complementarity in my work. The mathematics of quantum mechanics has this structure built into it at the foundational level. It's not a limitation we might someday overcome. It's a property of what quantum states are. Now we come to entanglement, which is the strangest confirmed fact in all of physics. Two particles interact, say two photons created together in a specific process. They become entangled. Their quantum states are correlated in a way that persists indefinitely, regardless of distance. One photon can be here, the other can be on the other side of the galaxy. Measure the polarization of one, and you instantly know the polarization of the other, even though neither had a definite polarization before measurement. Einstein spent years arguing this was wrong, not because the predictions were incorrect, they matched experiment, but because the implications disturbed him. He thought quantum mechanics must be incomplete, that there must be hidden variables, properties of the particles already determining the outcomes, that we just hadn't found yet. He called the apparent instantaneous connection spooky action at a distance, and rejected it. In 1964, John Bell proved that hidden variable theories make different statistical predictions from quantum mechanics. The experiments, Alain Aspec's in 1982, and many more refined tests since, confirmed quantum mechanics. The correlations are real. They're not explained by pre-existing hidden variables. What entanglement does not allow? Faster-than-light communication. The correlations only become visible when you compare the two results, and that comparison travels at light speed or slower. No causality is violated. But something stranger than simple causality is happening. I can calculate everything entanglement predicts. I cannot give you a picture of what's physically happening. I say that not as an admission of defeat, I say it as precision. This brings us to the measurement problem, which is the foundational issue quantum mechanics still hasn't resolved. Schrödinger's equation describes how quantum states evolve over time. It's deterministic and smooth, like a wave flowing continuously through possibility space. But when we measure, something different happens. The wave function collapses to a definite outcome, suddenly, discontinuously. These two processes, smooth evolution and sudden collapse, are described by completely different rules within quantum mechanics. The theory doesn't explain why or when collapse happens. It doesn't specify what counts as a measurement. It doesn't say where quantum ends and classical begins. The measuring device is made of atoms. Atoms follow quantum rules. So why doesn't the measuring device enter a superposition of measured spin up and measured spin down? Schrödinger himself illustrated this problem with his famous cat thought experiment. Put a cat in a box with a quantum-triggered device. According to quantum rules, before you open the box, the cat should be in a superposition of alive and dead. Obviously, cats are either alive or dead. So where does the superposition end? The theory doesn't say. The Copenhagen interpretation, developed largely by Bohr and Heisenberg, says, don't ask. Use the formalism to predict measurement outcomes. Don't ask what's happening between measurements. The question has no answer. The many worlds interpretation says the wave function never collapses. Every time a quantum event could go multiple ways, the universe branches. Every possible outcome happens in different branches. We experience one branch. The others are equally real. Pilot wave theory says particles have definite positions at all times, guided by a wave. Superposition and uncertainty are epistemic, about what we can know, not ontological. Each interpretation uses the same mathematics and makes the same predictions. None has been empirically distinguished from the others. This is an open question. When I built quantum field theory, combining quantum mechanics with special relativity, I was working at the mathematical level. I wrote a relativistic equation for the electron. The mathematics required an antiparticle, same mass, opposite charge. Nobody had seen one. My equation said it had to exist. Carl Anderson found it in 1932 in a cloud chamber. That's what the mathematics was telling us. And quantum field theory, the framework that grew from that work, makes predictions of extraordinary precision. The magnetic moment of the electron, predicted to 12 decimal places, confirmed to 12 decimal places. The most precisely tested theory in the history of science. And yet, quantum field theory breaks down when you try to include gravity. Einstein's general relativity, the theory of gravity, spacetime, and cosmology, is not a quantum theory. At the scales where both should apply, the Planck scale, deep inside black holes, at the moment of the Big Bang, we have no theory that works. We have candidates, string theory, loop quantum gravity, none confirmed. The standard model of particle physics, the quantum field theory that describes all known particles and forces except gravity, doesn't explain dark matter or dark energy, which together account for roughly 95% of the energy content of the universe. The measurement problem is unsolved. We know more about quantum mechanics than about any other framework in physics. We understand less about what it means than about almost anything else. Everything made of atoms, every piece of matter, every interaction, every chemical bond, every biological process, operates according to quantum rules at its foundation. The solidity of your chair, the chemistry of your metabolism, the light from distant stars, all of it runs on this framework. The universe, at its deepest accessible level, is probabilistic. Particles don't have definite properties until interaction forces them to. Distant entangled particles are correlated in ways that aren't explained by any mechanism traveling between them. When I was young, I believed that understanding the mathematics meant understanding the physics. I still believe the mathematics is right. What I've learned is that understanding the formalism and understanding what the formalism means are two different things. Quantum mechanics gives us the first with extraordinary precision. The second, what it means that this is how the universe operates, is a question I've thought about for my entire life. I don't think it's been answered. I'm not sure the concepts we currently have are adequate to answer it. That's not a limitation. That's an honest description of where we are. And it's an invitation to keep going.